Hi, and welcome to the 25th anniversary of the Computer Science Department at Aarhus University. My name is Kasper Larsen. I'm a full professor at the department where I head the Algorithms, Data Structures and Foundations of Machine Learning Research Group. Historically, the focus of our research group has been on algorithms and data structures. Algorithms are basically recipes for how to solve problems efficiently on your computer, whereas data structures are recipes for how to structure and store your information so that you can search in it efficiently. A concrete example of a problem that we have designed efficient algorithms for is predicting flooding in the event of either heavy rainfall or sea level rise. To do this, the input that we use is a digital model of the surface of the Earth, which consists of height measurements at a very fine granularity. For instance, one height measurement of the surface of the Earth for every square meter in Denmark. From this digital model, we can then compute where water will gather either in the event of heavy rain or sea level rise. When computing such flooding from digital elevation models, it's very important that you have high resolution data. Here on the left, you see the Danish island of Manø, where we have computed flooding in the event of a sea level rise of 2 meters. This model that we used here is a very low resolution model, and you can see that the entire island is flooded. If you instead look over here on the right, you see the same computation but on a model with a much higher resolution. And here you can see that the island is not flooded. So what happened here is that the island of Manø has a dike all the way around, and this dike is very narrow. It's only a couple of meters wide. So what happens on the low resolution model is that you don't even see the dike in the data. So it looks like there's no dike, and therefore the sea level rise would cause the entire island to be flooded. Now the problem with using such high resolution models is that these models are really large. For instance, a modern model of Denmark has more than 10 billion measurement points. This means that the data set that you're computing on is so large that it cannot be stored in the RAM or random access memory of your computer. This means that while your algorithm is running, most of the data has to reside on slow secondary storage, for instance, a magnetic hard drive. The problem with storing your data on a magnetic hard drive is that accessing the data on a hard drive is up to 1 million times slower than accessing data that's in the RAM. To fully appreciate the difference in the time it takes to access data in RAM and on a hard drive, imagine that you're frying an egg in your kitchen. If accessing data in your RAM is the same as getting salt for your eggs in the kitchen cupboard, accessing data on the hard drive is basically the same as walking all the way to the Dead Sea to get your salt, which of course I did. What this means for algorithms design is that the running time of your algorithm as your dataset size increases starts increasing steadily until a certain point where it explodes. The reason for this explosion is that your dataset size exceeds the size of your RAM, which means that most of your data has to be stored on a hard drive while you're computing on it, and suddenly your algorithm gets 1 million times slower. Now, as an algorithms designer, what should you do to alleviate this problem? Now, if accessing data is like walking all the way to the Dead Sea to get salt for your eggs, what should you do? You should, of course, bring home a lot of salt. In fact, this is precisely what happens when you read data from a hard drive. Whenever you read a data element, think of this as getting a pinch of salt. You don't get just one data element, but you get a whole block of millions of consecutive data elements. Think of this as a whole bag of salt. Now, what your algorithms should do is, of course, to try and make the most of this data, compute on all the data that you just got before you go and get more data on the hard drive. Algorithms that do this are called I/O-efficient algorithms. Designing such I/O-efficient algorithms has been a huge focus area of our research group. In fact, our research group hosted a Center of Excellence by the Danish National Research Foundation called Medalgo. The focus area of Medalgo was in particular to design these I/O-efficient algorithms. And actually, when the center concluded, the final evaluation report said that Medalgo was the world-leading research group in designing I/O-efficient algorithms. But now that researchers have been designing faster and faster algorithms and data structures for decades, at some point we got to ask ourselves, is there a limit to how fast we can solve these problems? Like for instance in physics, the speed of light is a limit to how fast anything can move. To better understand this question, let us have a look at an example of a data structure problem. So imagine that you're storing a database of cars for sale. So each of these cars have different properties. For instance, the price of the car and the mileage, or how many kilometers they have driven. And when you're storing such a database, what you want to do is support search queries on the data. For instance, a user could ask how many of the cars cost between 80,000 Danish crowns and 240,000 Danish crowns while having a mileage of at most 120,000 kilometers. In this concrete example, there are 3 cars satisfying the search criteria, so the answer to the search query is 3. Now, if you've had a course on algorithms and data structures, then you know that we analyze the performance of a data structure by writing down a mathematical formula that describes how much work it needs to do as a function of the input size. So for instance, if you're storing n cars in your database, then the fastest known data structure for this example data structure problem will answer these search queries by performing the logarithm of n squared many operations. Now, you can of course ask yourself, is this the fastest possible? Can we hope to design a faster data structure in the future, or is there a limit to how fast such searches can ever be performed? The very first data structure lower bound dates back all the way to 1989, where Fredman and Sachs managed to prove that any data structure that can support search queries, counting the number of cars that satisfy your search criteria, any such data structure must spend at least the logarithm of n divided by the logarithm of n many instructions or operations to answer your search query. Now, it took another 15 years before this bound was improved, where Petrasco and Demain in 2004 managed to prove that any such data structure must spend at least the logarithm of n many instructions. Finally, another 8 years later in work of my own, I managed to prove that any such data structure must spend at least the logarithm of n squared many operations to answer such search queries. Now, if you remember, the data structure that was already known, the solution that people have come up with, also spends the logarithm of n squared many operations. Which means together, we now know that this data structure is the best possible. We can never hope to improve over it in the future. And actually, this work here, this lower bound, was acknowledged by the community with a Best Paper Award. And in fact, even to this date, the logarithm of n squared lower bound that I proved in my work is still the strongest known lower bound for any data structure problem. This means that at Aarhus University, we are still world leading in proving data structure lower bounds. Looking forward from here, our research group was recently renamed from Algorithms and Data Structures to Algorithms, Data Structures and Foundations of Machine Learning. This means that we recently started looking also at questions in theoretical aspects of machine learning. Such questions could be, for instance, how much training data is necessary to train accurate machine learning models? How fast can we train machine learning models? And can we identify cluster structures in data? These are questions that we look very much forward to addressing in our research group. And with those words, thanks a lot for watching and have a very happy anniversary.